video that hopefully clarifies some concepts that you explored in the PhET lab. You can also use this to help complete your PhET lab document. Hopefully it's helpful. If you have any questions on it after watching the video and working through this in class, please leave a comment on your Google Classroom or email me or talk to me in class. So I'm just going to read through this and work through this with you together. All right, so it might be a little bit of a long video, but just stick with me at least in the beginning. All right, so we are going to first experimentally determine K, which is the spring constant, okay, for a given spring. I am going to do this for a spring that is different than the one I asked you to do in the PhET lab, just so that our numbers aren't identical, but the process for collecting our data is the same. And then 2, you're going to look at the energy stored in a spring using this equation for a elastic potential energy. Okay, and we are going to look at Hooke's law at the beginning of this. So Hooke's law states that the magnitude of the force F on the spring and the resulting deformation, or the displacement X, are proportional to one another, where K is this thing called the spring constant. So we talked about this a little bit in class. Spring constant is a measure of how much force, or how much, the spring constant is a measure of how much force is required to displace the spring a given amount. All right, so the force required to stretch the spring has a magnitude F equals Kx, and we are going to create a force versus displacement graph to determine what the spring constant is in the PhET simulation. So the first thing we're going to do is we're going to click on this link, we're going to select lab, and we are going to do the following. We're going to leave the spring constant on its automatic setting, which is the third tick from the left from small. So 1, 2, 3. This is default. You shouldn't touch this, but because I want my numbers to be different than your numbers, I am going to move this over so it's the third tick from the right. Okay, so yours is you're not going to touch this, but I'm going to move it so that my numbers that I'm about to get are a little bit different than yours. And watch how when I change this spring constant, the diameter of this spring changes. So the larger spring constant, larger diameter, it's going to require more force to compress this than a small spring constant. All right, so I'm going to collect my data for this spring, this unique spring. It's going to be different than what you have on your data table, but that's fine. Next, we are going to leave the spring constant on, turn damping to lots and select the following boxes: displacement / natural length and movable line. So I get to this point, you know, the movable line isn't that handy, honestly, I realized later on. But what we're going to be doing is we're going to be collecting information here for this data table, where you are going to vary the force acting on the spring and measuring the displacement. All right, so the reason that I've put this table as displacement and force is so that when we enter this on the Desmos graphing calculator, we get better result. We get a force versus displacement graph. All right, so although we're going to be varying the masses, which is going to vary the force, and measuring the displacement, this is how I want the table set up. All right, so the first thing I'm going to do is I am going to change that to lots, and I'm going to hang I'm going to start with 100 gram mass, okay? And when I hang it from here, I see that it quickly comes to rest, and that the spring, which originally is located here when no force is added to it, is now deformed and stretches a little bit. This green line is the displacement of the spring. And so I can use this measuring tool to find the displacement of the spring if I measure from the starting point of the arrow to the tip of the arrow. And this ruler is in centimeters, and I'm going to be recording my displacement in meters, so we just need to do a quick little conversion. Quick little conversion here. And so what I'm getting is I'm reading this as 11 centimeters, so 0.11 meters. Okay, so I would come here and I'd say the displacement is 0.11 meters, you know, that's already given. And the force, because I am because I am hanging a 100-gram mass, I can calculate my force using the following equation. So I'm just going to pull up this little whiteboard, and I know that the force acting on the spring is equal to the force of gravity, which is my mass multiplied by the gravitational acceleration. And so I know my mass is 100 grams, which if I convert that to kilograms, where there's 1,000 grams in a kilogram, and I do that multiplication where the grams cancel out, I end up with a number that is 0.100 kilograms. And so when I plug in my value for mass, I'm going to use the value in kilograms. So I'm not really minding the significant figures here. And 9 times 9.81 meters per second squared. And what that will do is that will give me a value for force in units of newtons, because a kilogram times a meter per second squared is a newton. And so the force of gravity here is going to equal 0.981 newtons. All right, and so on my chart, on my table, 0.981 newtons. So when I exert a force of 0.981 newtons on the spring, it displaces the spring 11 centimeters or 0.11 meters. Okay? Now I'm going to do this for, I'm just going to vary the mass, and I'm going to record the corresponding displacement. And so the next random mass that I chose to do is 120 grams. So when the 120 gram mass is hanging from the spring, I get a value that is like 13.5 centimeters, or 0.135 meters. 5 meters, and then that was measured to that. So I'm going to come back here and using the same type of calculation, but now my mass is, now my mass is 120 grams or 0.12 kilograms. Using that same equation I calculated for the force hanging on the spring. I've done this already, I've done this math already, so I'm just going to plug it in, 1.1772 newtons, okay? All right, now this might be, this is a lot of significant figures, but it's going to produce a better, some better data points for our graph later on. And so I do that again for 140 grams. So just randomly picking some numbers here that I've done this already. So this is so I'm not going to take I'm not going to take that much time to measure this, but it's 15.5 meters. That's or 15.5 centimeters. That's what I'm getting here. It's a little bit hard to see, and so 0.155, so 15.5 centimeters. And the resulting force exerted on the spring when you hang 140 grams is 1.3734 newtons, all right? And I'm just going to fill in the rest here because I've done this. 0.195 meters when I hang 180 grams, or when I exert a force of 1.7658 newtons. And when I hang 210 grams, I get a displacement of 0.230 meters. That resulting force acting on the spring is 2.0601 newtons. And then finally, if I hang a mass of 280 grams, or if I exert a force of 2.7468 newtons, I get a displacement of 0.310 meters. And so the next thing we're going to do once you've filled out this data table, and your data table will look very different than mine because you're going to be using a different spring constant. You're going to be using the spring constant right here, I believe. And you're just going to pick your own numbers, your own masses, okay? As you vary the mass, you vary the force exerted on the spring. You know, that's one way to do it. Additionally, you could keep the mass the same and you can change the force of gravity. All right, but that's a little bit, you know, of a different approach, but it achieves the same idea. You vary the force acting on the spring. But you take these values and you click on the link here for the graphing calculator, and you are going to make a table. All right, so you're going to insert a table, and then you're going to simply put your values for the displacement in the x column and your values for the force in the y column. And I already did this over here. This is what I've got. I've got all the values from this table. Got all the values from this table into this Desmos. And they're plotted here. And now what I want to do is I want to create a line of best fit. And we already know that the relationship between the spring constant, we know that the relationship between the force and the displacement is a linear relationship. It's a directly proportional relationship. We're simply looking for the slope if we were to think of it as a line. And so I've already plotted my force and my displacement. And so my y-axis can be thought of as my force values in newtons. My x-axis can be thought of as my displacement in meters. And so now I simply want to know what the slope of this is if I created a line of best fit. All right, and so to do that, you are going to type in y1 is approximately, mx1. And when you do that, you are given some values down here. You are given values for the r squared, which is like how well this line fits to the data points, which is the closer this r squared is to 1, the better the fit. And you're given what the m is. So we're creating this slope. The m is 8.9047. And so I'm just going to take that number, 8.9047. That is my spring constant. That is the magnitude of my spring constant for this given value. So 8.0, I already forgot it. 8.9047. 8.9047. All right, and so the units here are going to be the units of the slope, which are going to be the change in the y, which is in newtons of meters, over the change in the x-axis units, the change in my y-axis units, which is newtons, over my change in x-axis units, which are meters. So newtons over meters. Okay, newtons over meters. And so that's the spring constant that I'm going to use when I start to fill in this part 2 data point, or this part 2 table. So now it says you will show that the mass is dropped starting from the natural resting. You will show that when a mass is dropped starting from a natural resting point of the spring and travels to its maximum displacement, the total energy stored in the spring is equal to the change in gravitational potential energy. And that's going to be something that we're going to look at using this table too. So it says reset the simulation and turn damping to none. It may be helpful to select the boxes next to displacement / natural length and period trace. It may also be helpful to select slow at the bottom right hand corner. Complete the following table. Fill in the following table for a hanging mass of 210 grams. The mass should be relieved so that the end of the spring is at the blue dashed line. This is the initial condition. The final condition is at the point of maximum displacement. What I mean by this is, we're going to change our damping to none, and we are going to click on this period trace, which is helpful. I am going to adjust my mass to 210, which is the mass that I ask you to use in the simulation. And I'm going to get different results from you because my spring constant is a different value. And so what I want you to start with is, clicking slow helps, to attach this mass, but don't push it up, don't pull it down to start. Just simply put it on the spring so that there's no displacement of the spring to start. And then what you'll see is when you let it go, it's going to travel down and then up. Okay, there's a few things I want to mention. This trace can be a little bit confusing because as you saw, it started tracing it midway down its path. All right? Another confusing thing that you might encounter is that the trace is tracing from the middle of the spring. It's locating the center of mass of this mass, and that's where it's making the trace. Okay, so the lowest point on this trace is not the lowest point the spring is not the lowest point the mass travels, it's the lowest point the center of mass travels. And this highest point is not the highest point that the center of mass is, it's the highest point, or it's not the highest point the mass is, it's the highest point the center of mass is. So it's a little bit confusing. But this is my initial condition right here, where the mass is resting, okay, and there is zero displacement. So let's talk about this. The mass has a value of 210 grams, so 0.21 kilograms. Okay, we're going to be using kilograms for our mass values. The displacement is 0. The displacement of the spring is 0. The height, this is a little bit tricky, and what we'll be learning is that the height really doesn't matter where you decide to measure as long as it's consistent for your initial and final conditions. So what I mean by that is when you pull this ruler up and you measure the height, you can do it a couple different ways. You can measure the height from the top of the mass, okay, to this height equals 0. This is an identified 0 point, which is pretty handy. And so I would use this if I were you. And I would say that we're going to call this the height of 0. And you could either choose to measure from the top of the mass, like I have the ruler set up, or you can measure from the middle of the mass, which is where this black line trace is, and they're going to give you different numbers. Okay, they're going to give you different values, but what we'll see later is I'm not really interested in the total potential energy at the beginning. Or the total gravitational potential energy at the beginning. I'm interested in the changing gravitational potential energy. So as long as your measurements are consistent for your initial and final measurements, as long as you're measuring from the same place, it's not going to be a big deal. And so for this, I'm going to measure from the top of the mass, and I'm going to see that that is 95 centimeters. So the initial height as measured from the top of the mass is 95 centimeters. So the initial height is 0.095 meters. All right, my K is this number, same K I calculated earlier. There's no easier way to do this. The spring constant K, there's no easier way to do that, is that. And my velocity at the top is 0. So when I start off, I know that I let the spring run, but when I start off, this is where my initial point is. Okay, my velocity is 0. All right, so my velocity is 0 here. So I'm going to go back and write 0 meters per second. So now what I'm going to do is I'm going to switch over to the iPad, and I am going to calculate the potential energy due to gravity. All right, so my potential energy due to gravity equation is mass times gravity times height. And because we're talking about this as my initial, I'm going to just put a little I subscript. And so my mass, it doesn't change mass values, G doesn't change, but my height initial changes, so it's important that I denote that this is my initial height that I start with. So my potential energy due to gravity initial is equal to the mass, which I can find as 0.210 kilograms, times G, 9.81 meters per second squared, times my height, which is 0.95 meters. So if I plug all those things into my calculator, what I end up with is a potential energy of 1.957095 joules. Kilograms times meters squared over seconds squared, or a Newton times a meter, okay, is a joule. So I'm going to round this to, that really should be 0.950. I'm going to round this to 3 sig figs. So my potential energy due to gravity initial is equal to 1.96 joules. Okay. So back to the computer. Back to the computer, 1.96 joules. All right, so now my elastic potential energy equation is 1/2 kx squared. But because my displacement, my x value, right, my displacement is my x value, because that is 0, I know that my entire elastic potential energy is 0 here. And I know that my velocity is 0, so my kinetic energy is 0. And so simply my total potential energy, is all in the form of my gravitational potential energy, and it is 1.96 joules. Now, my final conditions. Final condition is at the point of maximum displacement. So if we go back to this and we click play, maximum displacement occurs right there. Whoops. I'll play it through again so maybe you can see a little bit better. Goes up and then goes down there. And so I'll press again, I'll press play when it gets to, all right, so if I slowly progress this, this is my point of maximum displacement, where the middle bar is at its lowest point. So the middle of the center mass, that's its lowest. So I'm going to pause the simulation here, and I'm going to go to start collecting data. My mass is the same, nothing changes, right? My mass is the same. My displacement is now some value, okay, because this green arrow shows me my displacement, and I can measure the displacement of the spring. So my displacement is 45 centimeters, 45.0 centimeters, or 0.450 meters. Wait, that's not right. It's 46 centimeters, 46.0 centimeters, so 0.46 meters. Okay, my height, this is what was confusing a lot of students, is my height, because I measured from the top of the mass earlier to determine the height, I need to do that again. I need to measure from the top of the mass again to determine my height. And so my height here, okay, my height here is 49 centimeters. So 0.490 meters. Okay. My K is the same as it was earlier. Something I do want to point out, there were a lot of students who had, when you guys have a different spring constant, the mass hangs a little bit lower and you're not able to get the ruler down as far as you were. Just remember that, you can choose, like if I were to measure not starting at 0, the height of this thing, this is starting at 20 and going to 69. And so the difference in 69 and 20 is going to give me my height of 49 centimeters. So just remember and make sure you're doing that, because this height isn't 69 centimeters, it's 69 centimeters minus what I start with, where I when I mark the ruler. Okay, so that's something that I noticed a lot of students were having trouble with, figuring out what the height of the hanging mass is when you can't move the ruler all the way down to the bottom. All right, so what I want to point out, something real quick, the displacement here is equal to the difference between the initial height and the final height. 950 meters, or 0.950 meters, minus 0.490 is the displacement, which makes sense because when the mass was at its original location, right, when its mass was at its original location and the displacement was 0, boom, its height was 95 centimeters. As it continues to go down, its change in height is equal to this displacement. Its changing height is equal to the displacement of the mass. So the difference between the initial height and the final height is the displacement. That's something that I just don't think a lot of us were getting. And so that's another way to check your measurements, check your values. Another thing I want to point out is that just like a ball thrown up in the air has a velocity of 0 meters per second for a very brief moment in time because it's changing its direction, so too does this oscillating mass. As it goes up and it goes down, as it changes its direction at a very brief instant in time, right there, it has a velocity of 0. It has no kinetic energy. And the same is true for when it changes direction at the bottom. It has no kinetic energy. Okay? It has no velocity. So at its final location where its displacement is the maximum, its velocity is 0 meters per second. So the potential energy equations are going to be calculated. I'll do that on the iPad again. Switch to the iPad now. All right, so the potential energy due to gravity final is equal to mass times gravity times height final, so the final height. So let's see. Mass is still 0.210 kilograms. G is 9.81 meters per second squared. And my final height is 0.490 meters. So my potential energy due to gravity final is going to be less than what I started with, which makes sense because I'm lower and my mass is the same and I'm still on Earth, so my acceleration due to gravity is the same. And so my potential energy due to gravity final is 1.009449 not newtons, joules, because a joule is a kilogram times a meter squared over a second squared, or it's a newton times a meter. Okay, and so to round this to 3 sig figs, we get 0.10 joules. Okay, and end iPad. 1.001 joules. All right, I guess I should have just kept it up because now I have to calculate the elastic potential energy. All right, so the elastic potential energy, elastic final, is going to equal 1/2 kx squared. We know that the K value is 8.9047 newtons over meters. And my displacement is 0.460 squared. when I do this in my calculator, I get 0.9421176, rounding it to 3 significant figures. My potential energy elastic final is equal to 0.942 joules. If we look at the units here, I end up with newtons times meters squared over meters, and that gives me newtons times meters. Wow, that's really sloppy. Hold on. Newtons times meters. Let me just zoom in. And a newton times a meter is equal to a joule. Okay, that's how I end up with this joule. So back to the desktop. 0.942 joules of energy for my elastic potential energy final. And so again, my kinetic energy is 0 because my velocity is 0. And so I simply add up the potential energy due to gravity and the potential energy elastic due to the spring. And 1.001 plus 0.942. Whoops, I'm not keeping these to their correct significant figures. But if I were to add them before rounding, this is what I would get: 1.009449, 1.01. Yeah, that's what it should have been. Plus 0.9421176. I end up with 1.95 joules. All right, so the difference between 1.96 and 1.95 is due to errors in calculating the displacement and errors in the spring constant. But they are pretty close to one another. Even if your values are like 0.5, that's pretty high. Even if they're like 0.1 and below, similar, I think we're okay. And so the idea here is that the energy gets transferred between gravitational potential energy and elastic potential energy. So I started off with all my energy and potential energy due to gravity, and as the spring traveled down, it lost some of that potential energy due to gravity, but there was an increase in the elastic potential energy, the spring's elastic potential energy. Okay, and so we did these calculations to confirm that the total energy stays the same. All right, where is your zero line? What's another location you could have? You could have the zero line. You could have put the zero line without put the squiggly away. Yeah, you could have put the zero line. How would you change your PE? How would that change your potential energy due to gravity values? Right, so go back to this and think about, okay, I measured the height from here. How could changing the height have altered my gravitational potential energy values? And in what way? If I increased the height, the zero height line, would that have increased my potential energy due to gravity initially? Or would it have decreased my potential energy due to gravity initially? All right. And would it have mattered in any of the calculations? I guess that's not the question, but that's a question. What is the change in gravitational potential energy? What is the change in elastic potential energy? Remember, change is measured as final minus initial. Okay. So you should be able to do that. During the mass's journey, does it ever have kinetic energy? Where do you think kinetic energy is the most? Remember, it starts, yeah, well, you can do that one. Now you're going to calculate the velocity of the hanging mass as it's halfway down its path when the displacement equals displacement max divided by 2. All right, so use table 3 to help you calculate the velocity of the mass halfway down its path. This is a little bit complicated, but if you follow the steps that we just took from above, you should be able to fill this in. All right. If you are savvy about it, you know that the initial conditions here are going to be the same initial conditions I got here. Right? Nothing is changing. Nothing is changing. And you know that my final conditions are also the same. Right? The only thing that is changing is what happens halfway down here. But even that isn't too difficult to figure out because we can pretty much look at this table. And so we're going to use this table to help us identify the velocity of the object halfway down its path. So, you know, just looking at this, it's got some motion, so we know it has some velocity, we know it has some kinetic energy. And so we're going to use our understanding of the conservation of mechanical energy to figure out what the velocity is, which is kind of a cool idea. That's about halfway down. That's about halfway down. That is about halfway down it's from its maximum displacement. Okay, you know, it makes a little S on the trace, and its total displacement should be something like 23 centimeters. Let's see if that's about right. No, that's not correct. Why is that not correct? That's halfway down. Okay. All right, so if the final displacement is 46 centimeters, then I know that halfway down its displacement is going to be 0.230 meters. Okay. I know that the height is going to be between 0.950 and 0.490. Or I can subtract the displacement from the initial height. Either way, if you find the middle between 0.490 and 0.950, or if you add on, if you subtract 0.230 from 0.950, you're going to find the midpoint. Okay, 0.720. So 72 centimeters. Right, I'm doing all this on this table because I'm asking you to figure out the mass, the velocity of the hanging mass as it's halfway down its path. And so if we know halfway down its path is when the displacement maximum is half, then I know that my displacement is going to be 0.230 meters, and therefore my height is going to be my initial height minus my displacement, which is 0.720 meters. My K stays the same. My velocity is a big question mark. We'll come back to this. And now I'm going to calculate my potential energy due to gravity, and I'm going to calculate my potential energy elastic, and I'm going to do this all on the iPad. So let's go over the iPad. All right. Here we go. Potential energy due to gravity halfway down. Okay. Is equal to mass times gravity's, the acceleration due to gravity times height halfway down. Potential energy due to gravity halfway down is equal to the mass, 0.210 kilograms, times g, times the height halfway down. And so the height halfway down is 0.72. So plug that into the calculator. $1.483272 joules. Okay, so when I plug that into the table, it's just going to be 3 significant figures, 1.48 joules. Now I'm going to calculate the elastic potential energy. So the potential energy in the spring halfway down, which is going to be 1/2 kx squared. And so that is 1/2 times the k, which is 8.9047 newtons per meter, times the displacement, which we said is 0.23 meters, and I'm squaring that. Okay, 0.230 squared times my potential energy is in the spring is 0.235529315 joules. Okay, I'm going to round that. 0.236 joules. So here's the deal. You have the total energy equals what we started with, which is 1.96 joules. And that total energy is the same as the energy halfway down. And that energy halfway down is the sum of the potential energy due to gravity plus the potential energy elastic plus the kinetic energy. And so if I know what the sum of the potential and what the sum of the gravitational potential and the elastic potential is, then I know what the total is, then I can figure out what the kinetic energy is. Okay, and I know just by looking at these two numbers that the sum of 1.483272 and 0.235529315, I know that is equal to, just recording, good, is equal to, equals 1.71881315 plus my kinetic energy, and that's all equal to 1.96 joules. So if I subtract 1.71881315 joules from both sides, I can't write it all. Then I get that my kinetic energy is equal to 0.241198685 joules. Way too many significant figures, but I'll just keep it for now. So I know that my kinetic energy has to be that amount. And I know that my kinetic energy equation is 1/2 mass times velocity squared. So I can set those two equal to each other, and I can say that, I guess I'm just going to solve for v. That's like the easiest way to do this. Multiply both sides by 2. 2ke divided by m. And then square root the whole thing. Okay. Is equal to my velocity. Now, if I know that my kinetic energy is this number, 0.241198685 joules, and I know that my mass is 0.210 kilograms, then I'm doing this in my calculator. I can find out that my velocity is equal to 1.515628692 meters per second. Or if I round to 3 significant figures, 1.52 meters per second. Okay, back to the screen. Plug in all these values. Potential energy due to gravity is equal to 1.48 joules. The elastic potential energy is 0.236. My kinetic energy was found to be I'm rounding this, 241. And my total energy is 1.96. That's the number I used. And my velocity is 1.52. Okay, meters per second. Here we go. All right, so we can describe how we calculated the mass, calculated the velocity of the mass as it was halfway down the path. Okay, one of the things that I skipped over was predict the maximum displacement of a hanging mass of 400 grams. This one is going to require me to do a little bit more work, but on the iPad. But what I want you to try to think about is that the initial position, the initial height, and the final height, the difference between them is the displacement. That is a key thing in writing out the equation for predicting the maximum displacement with a hanging mass of 400 grams. And so I'm going to make a whole separate video to answer this question because it's a little bit complicated. But if you're looking for a hint, that's the hint. The displacement of the spring is the difference, in this case, between the initial height of the spring and the final height of the spring, or the initial height of the mass and the final height of the mass. The changing height is the displacement. All right, so there'll be another video linked below at some point that will go over how to answer this question. But the rest of this is here for you. All right, have a great day. Like and subscribe. Bye.